right, the recorder's on, so I'm going to get the lecture started. I know some people are still trying to stream in, so I'm going to talk about something that's not too related to this class. The college, ARC, is going to try to see if we can get funding from CCC Maker, which is a grant. This is a grant, for maker projects or maker space. How many people know what is a maker space, or what is the maker culture that is kind of popping up, left and right? Okay.
I know it, but you were talking about like last week in this class.
Oh, I did?
Yeah.
Yeah. But I haven't shown you guys the actual
Whatever day was this one.
recommend. The self-study is almost done, so I can show you the self-study for right now. So we have. Okay. There we go. All right. So what I haven't really shown you guys is the self-study document that is being done at this point. So right now, the three of us, the three stooges, so to speak, are working on this particular self-study. So we're trying to, basically get past the first hurdle to possibly, get, some grant money to have our own makerspace in ARC. So I think that's really great because it means, for the next few years, if we can actually get a funding, there will be an expansion of our current makerspace, which is basically room 309, the Design Technology Lab. What I do notice is, when people mention Maker or Hacker Lab and stuff like that, they think about what? They think about 3D printers, they think about laser cutters and whatnot, but they don't think of software. Okay, because everything is kind of material, and people look at maker, the maker culture, like this is something new, this is great, people being innovative, being inventive, but they're forgetting Steve Jobs, Steve Wozniak, all of those people who were actually innovative to basically get us up to where we are now in terms of computer science. Without computers, or without computers driving the what is behind the scenes, the 3D printers wouldn't be a possibility. The software to feed 3D printers will not be a possibility. So I just want to show you this because I think there's a lot of potential for computer science students and also the computer information science department to participate in the ARC Maker movement. I know it's way too early to really say anything about it, but I think there's a lot of possibility because they're trying to make all of these newer equipment for fabrication, for 3D printing, and they don't have, they have some people working right now, so you're working on those projects, but we don't have nearly enough software people, enough computer science people working on those projects. So just something for you guys to kind of keep in mind if you'll be here for the next 1 or 2 semesters. This is something that you can kind of look into, think about, and if you're interested, go to the Computer Science Club meeting. So I'm just plugging for the club. All right. Okay, so there's that. For this class, what we'll do today, you guys remember what I said we would do today? No, we have no idea what we're going to do today. Okay, what we have done so far with cisp440 was we talked about propositional logic, right? We talked about how we can have inference, right? So our inference rules, are they syntactic or semantic? Do they care about the meaning of the operators, or are they really just doing some pattern matching? They're like, oh, if I see this pattern here, I can apply it to the well-formed formulae, and so I end up with this particular well-formed formulae. Which one is it? Syntactic or semantic? Syntactic. Okay, very good. Okay, because the idea is we want to use propositional logic or propositional calculus to automate theorem proving. That'll be great because we want to be able to prove the correctness of programs autonomously, so that we don't have to hire someone to basically do all kinds of really tedious proof for 20 years just to prove that the SSL library is now bug-free. Okay, yep.
Just to diverge a little off of that, can you please go to the propositional page and then go to the zeta transformations? So I have a question.
Okay, so you want to look at this part or
A little lower.
for these guys?
A little lower. No, what's that? Can you go up there?
Did I miss?
Let us take a look at zeta transformation. Go a little up.
Up?
Right there. So the first two bullet points, can you explain that to us?
This one?
Both of them.
Okay, this one and this one?
Yes. Please.
Okay, so this particular transformation rule has an empty set on the left-hand side of the inference symbol, right? But there's nothing on the left-hand side, which implies it is an empty set, which basically means you do not need to know anything at all, and then you can just grab any well-formed formula and say, well, this well-formed formula or the negation of this well-formed formula together, the disjunction itself has to be true. Okay, I'll give you an example. So let's just say that your A or your alpha set is 0, 1, those have to be here. Then you have P, Q, R, and then you have the Greek symbols. You have phi, psi, rho, and rho. Okay, so let's say this is your alphabet. This is your alpha set. Okay, and then we have the usual things in the omega set, which are usually your Boolean operators. So we got negation, conjunction, disjunction, implication, equivalent to, those are our operators. Okay. So what this rule is saying is, you can, as long as it is a well-formed formula, that well-formed formula and the negation of that well-formed formula has to be true. In other words, I don't even care about what is in iota. I don't even care about that. Okay. I can just take a look at this and go like, well, let's do something crazy here. Okay. And then take the negation of that and say that this implies, P, okay? I have absolutely no idea whether this has to be true or not, okay? But then I can take this as one well-formed formula, and that becomes my psi, right? Then I can say, oh, you know what? If I take this well-formed formula and then do a disjunction with the negation of the same thing over here, this well-formed formula has to be true all the time. The disjunction itself has to be true all the time. Does that make sense? Of course it makes sense, right? So that's basically what this formula is saying. Am I answering the question that you have? And that's why, this particular rule can generate an infinite number of expressions that is not going to help you to get to the proof that you need. Because you can go in the wrong direction indefinitely, and there's no bound. Okay, you cannot. There's nothing that will tell you, oh, it's time to stop. Okay, because this is not being productive.
So the second part is saying.
It's basically the converse of that.
Okay.
It's basically saying, if you take this thing, okay, whatever well-formed formula it is, and then you say, oh, this time instead of an or, we have an and then we say, oh, by the way, the negation of this and has to be true. Well, of course it has to be true, because the conjunction itself has to be false. Because one side of these two things, okay, has to be false. When you have a conjunction, you only need one false for the entire conjunction to be false. But when you negate the false, then you have true. Then it is always true. But is it useful? Well, in some cases, it is useful. Okay? In most cases, it is not useful. So it is a valid transformation rule, which means it is sound. It makes sense. On the other hand, is it really going to help you, finish your proof to show that a theorem is a theorem? Maybe, maybe not. And the problem is, a computer has no, there's no condition to tell a computer, to tell a program, to say, oh, stop, don't apply this anymore. This is not making any, and we are not moving in the right direction. Yep. Mm-hmm.
But then, when I get to the point that he says psi and not psi is always true, it just doesn't seem right because negation of that is always true.
Yeah, I think I miswrote here. So this means this is always true. Yep. I think the second paragraph, this one is not supposed to be there. because this one is always true. The negation of the conjunction is always true, but this part really should not be there at all. Okay. So I had a so I typed it incorrectly. Question?
No, it seems like it still holds true now.
This one is always true.
Mm-hmm.
This one is always true, which means you can take any well-formed formula and just say that well-formed formula is our psi, and then and then make this new well-formed formula and say this new formula. New well-formed formula is always true. And then you take that and then you reapply the same thing, so you get something that's bigger and bigger and bigger, but it's not going to help you. Do you see how you can repeatedly use this to generate, just keep generating more useless well-formed formulae? Yep.
Just to clarify, the second one, if it was not negated, since it's a disjunction, it would not be true.
Correct. So this one, which is not negated, is always false. So this one is, if I change this true to false, then the sentence is correct. So let me just change that first, so this way we won't have a problem when we read it again. Okay, so that should be it. Save and display. Okay, so I got it fixed because this one is always false, and that's why the negation of that is always true. Okay, good point. Good point. Any other questions regarding the transformation rules or the inference rules? No question? Okay, all right. So the biggest problem with this set of transformation rules is, even though it is sound, okay, it makes sense, but it's very difficult to automate theorem proving just using these rules, okay? Because if you only have these rules, how do you tell a computer using a program and prioritize which one to try first? Because especially on the ones like this, where there's an empty set on the left-hand side of the inference symbol, it means you can just pick any well-formed formula, plug it in here, and now you have another well-formed formula that is always true. But it's not going to be helpful. In most cases, it's not going to be helpful. In some cases it is, but not in most cases it is not. So that means if our inference rules look like this, it becomes very difficult to actually write a program to prove theorems. Now, how do you prove theorems? How many people in this class actually enjoys proving theorems in your math classes? Okay, so we have a minority, let's just say a minority of people in this class who who enjoys proving theorems. Why do you not enjoy proving theorems? That's the question, right? I mean, why not? How is that different from, say, writing programs?
Can't play with
It's
it.
not straightforward, okay? Yeah, go ahead.
Playing with
There-
it, made writing programs can be fun. Like you can
There
play
are
with it.
There are too many degrees of freedom. Okay? There are too many degrees of freedom. Which rule, which axiom do I apply next? Let's say this is algebra. Okay, so you can use algebra, rules and transform an expression to some other, expressions. But which one is going to help you to get to what you need? That's the question. There are too many degrees of freedom. So unless you have the experience, which helps you prioritize and say, well, from the look of this, I think these are the useful ones, so I'll try these first. But that's based on experience. It's kind of like a fuzzy thing, right? But when you write programs, it's a lot more constrained. What is the main constraints of writing programs? Why doesn't it? The syntax is one, and then the logic of the program is also very constraining. Something that's repetitive is going to have a loop. Now, you can choose between a do while, which is a post-checking loop, or while do, or you can choose a for loop, which is a shorthand of a pre-checking loop that has the initialization and the post operation included into the statement. But those are your only choices. If you have something that has branching, okay, in some cases we want to do this, in some other cases we want to do that, that's your conditional statement. You don't really have that much of a choice. Yes, if you really want to, you can also say, but I can use ternary operators instead of a conditional statement. Fine, you have two choices then. But when you're proving theorems, you have a lot more than that number of choices. So what do you choose to apply to the set of known facts in order to transform that into the theorem that you're trying to prove? It's really fuzzy. It's really hard to get a handle on those things. And that's why we feel that it's kind of hard, because we don't know how to proceed. We don't know which one to pick in order to move forward in the direction that we want to go. Is that making any sense? Is that kind of capturing why theorem proving in your math classes can be challenging? Okay, very good. Okay, so what we want to do is make automated theorem proving not as challenging, because if it is difficult for you, think about how difficult it is going to be for computer. Because this is not something that is about the speed of doing things. This is about prioritizing, choosing which transformation rules to use. So that's why we talk about the next topic. We talked about this already, which is CNF, or conjunctive normal form. So with conjunctive normal form, it does not even seem to be related to propositional calculus at all. This is just coming out of nowhere. How is this related to propositional calculus? Okay, so by itself, it doesn't seem to be related. Now, it does relate to some other fields. If you are in computer engineering and you need to fabricate logic gates, especially in the case of programmable logic chips, a lot of times they have a certain structure of gates. In other words, you have to transform everything into conjunctions. You have to transform everything into disjunctions, or the negation of conjunctions, or the negation of disjunctions. So from that perspective, there is some application of CNF in computer engineering. But in this class, what we are interested in is proving theorems. So why would this be helpful in proving theorems? This section here, we talked about this the other day already. This section basically gives you all the tools that you need in order to transform any well-formed formula into a CNF. I can give you something like this, okay? And we can transform that into a CNF. Is that okay? All right, so we can go through at least one example. I can use this as an example to show you guys how to turn this whole thing into a single CNF. Okay, but I want to talk about the next major concept first, before we try to talk about how to transform a well-formed formula into a CNF. So the next topic talks about resolution. Now resolution is really cool because it is a single inference rule. In other words, instead of that whole bunch of big huge collection of transformation rules, or inference rules, we only have one now. Okay? But in order to use only one single inference rule, we have to make sure that everything is expressed as a CNF, as a conjunctive normal form. So this is how CNF ties in with propositional calculus. If everything is expressed as a CNF, then we only need one single inference rule. Now, if you only have one single inference rule, you might think, well, we'll still have the degree of freedom issue, because then we have to choose which well-formed formulae to use to apply this rule to, right? And you still have that particular degree of freedom. But the answer to that particular question is it's not a problem, because you can only apply this rule so many times. After you apply this rule, inference rules, so many times, it can no longer come up with new results. Okay, if you're writing a program to do this automatically, then you can stop, because you can see that there are no new ways to apply this inference rule. If you reapply it, it will just generate something that you have seen already. So it gives you a definite way of getting out of that loop. Okay. But before we actually use this inference rule, we have to prove that it is sound. And this part here is a proof to prove that it is actually sound. So we'll go ahead and just go through the proof a little bit, because I think it is kind of important that we understand how to apply the Boolean algebra, in this case, to prove a particular theorem is true. So what we really want to do is to say that this particular implication is always true. Okay, so the conclusion here is it is always true. So it doesn't really matter what your phi is, doesn't matter what your psi is, or your rho is, okay? Stating that if this is true, this has to be true, the implication itself is always true. So we are trying to prove the soundness of this particular inference rule by saying this first. Okay, so how do we do that? The first one is really the application of the definition of implication itself, which is negating whatever is to the left-hand side of the implication. So we have a negation here, and this entire thing is whatever is to the left-hand side of the implication, and then the part to the right-hand side of the implication is preserved without any changes, but the two are connected with an OR. In other words, A implies B is exactly the same thing as not A or B. Any question about the first rule? It's just by the definition of implication. What about the second row? What are we doing with the second row? Well, on one side, we are just taking the parentheses away, because we have an OR, and then inside the parentheses we also have OR. Because of the associativity of disjunction, we can remove the parentheses so that we just say, okay, there's no big deal here. It is just one bigger disjunction. Is that okay? What about the other side? What did we do to the other side? We use De Morgan's law. De Morgan's law can be seen as a distribution of negation into components of a disjunction or a conjunction. In other words, we started off with a disjunction, we started off with a conjunction that is negated on the outside. So what we do is we distribute the negation to the stuff that is inside, but at the same time we have to turn the conjunction into a disjunction. That's De Morgan's law. Are there any questions about De Morgan's law? Okay, well, De Morgan's law is De Morgan's law. How do we know this law itself is valid?
Because it's an axiom.
It's an axiom, okay, but just because text says it's an axiom should not convince you that it is so, right? So how do you prove it? How do you prove an axiom? Well, in algebra, it's really hard to prove an axiom because you have an infinite number of values when it comes to numerical values. But for Boolean stuff, we just use a truth table. Okay, so this is a quick way to do it. All right, so we need to check whether text claim is right or not. My claim is De Morgan's law is right. Okay, that transformation is correct. Okay, what is the transformation? The negation of A and B in this case is really the same thing as not A or not B. Okay, that's my claim. I claim that these two expressions are exactly the same. How do you prove that these two expressions are exactly the same? Well, we look at all the possible cases. A and B are independent variables. So we say, okay, what if A is false, false, true, true, B is false, true, false, true. Okay? These four combinations are the only combinations that you can get when A and B are Boolean variables. Okay, so this is something that we can do in Boolean algebra that you cannot do in normal algebra, which is basically just exhaustively list all the possibilities and just say that for all possibilities, these two expressions end up with the same value. Okay, so what is the value for A and B being false? Okay, this is true, 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 because if at least one of those is a false, then the conjunction itself is a false, then the negated becomes true. So the only time this whole thing is false is when A and B are both true. Then A and B is true, not true is false. Is that okay?
Yeah.
Then we move on to this side and say, okay, A is false, not A is true. This is an or. If one side is true, the whole thing is true. So we know this is true. And on the second row and also on the third row, we know that one of them is false, one of them is true. So the negation of one of them has to be true. So we know that it is like this. And then on the last row, A is true and B is true. That means not A is false, not B is false. That also means that not A or not B itself is also false. So now we have shown that for all possible combinations of A and B, the first expression, which is having the negation on the outside of a conjunction, gives us exactly the same value as putting the negation into each component, but connecting the components by a disjunction. This is the proof. Okay, we can actually prove axioms in Boolean algebra, which is great. Is that okay? And then the other one is true as well. Okay, I'm not going to prove it, but if you're not convinced, you can prove it yourself. The negation of a disjunction can be expressed as the negation to each individual component, but then you change the disjunction into a conjunction. That's the other side of that's the other De Morgan's law. All right. So this is really useful stuff, not only for this class, but also for any class that requires the use of Boolean algebra and logic, because this is really just logic. All right, so getting back to our proof here, I applied De Morgan's law to this thing, and then we ended up with this thing here. Okay, so what do I do next? Well, what I do next is another application of De Morgan's law, because there's a disjunction here applied to a negation applied to a disjunction. So I applied the negation to the individual components, changed the operator from disjunction into conjunction. Same thing over here. We have a disjunction on the, we have a negation on the outside, a disjunction in the inside. So we apply the negation to both of the components. Double negation is canceling itself. And then we have a single negation to row. So that's why we have a not row here. But we also have to change the disjunction into a conjunction. So that's how we got from the second row to the third row. And then over here, this one is kind of interesting, because what I did is, instead of looking at psi all by itself, I say, hey, I can look at psi as psi and true. Is that okay? Can I just out of nowhere and say, hey, this is something, let's just add an and true to it. Would that change the meaning of that expression? No. Well, just because I said it's not going to change it doesn't mean it's not going to change it. Can you prove it? Yeah. How do you prove it? Truth table. Okay? You can use a truth table to show that we can add a and true to any Boolean value without changing the Boolean value itself. Okay? So with this class, we really need to make sure that we understand all of these things and and also the fact that they work. And we'll do the same thing with row here. So instead of just having row all by itself, we say this is row and true, okay? Which doesn't seem to be very productive, because it seems like, why would we do something like that? The next one is even worse. The next one is say, oh, what can be true? Let me see. Well, some kind of expression or the negation of that expression itself has to be true. In other words, I take this true and then I expand true into something that's even more stupid or stupider, because stupider sounds more stupid than more stupid. Okay, right? We're getting back to what we just started off with, but this is one case where it is actually useful. Okay, and then we do the same thing on the other side, just like that. We turn this single true into psi or not psi. Same thing. Are we still doing okay so far with this proof? So at this point, it seems like we're introducing some artificial additional thing that doesn't seem to have anything to do with the proof itself. So what about the next one? The next one is to take this expression and apply the distributive rule to the Boolean expression. So it becomes phi and psi by itself, which is here, and also phi and not psi, which is over here. So I basically apply two transformations, in one single step. I apply the distributive rule and also the commutative rule at the same time, because I changed the order. Okay, and then I do the same thing on the other side. So I basically just as some people would say, we just multiply out the whole thing. So now we have rho and not psi, or rho and psi. Is that okay? So once again, if you're not convinced that this can transform into this, all you have to do is to make a truth table in order to convince yourself. Now this truth table is going to be bigger because there are 3 independent variables involved, so it's going to have 8 rows. But you work on the 8 rows exactly the same way, because the 8 rows will exhaustively list all the possibilities, all the possible ways to combine rho and psi. Oh, excuse me, there are only 2 variables. I see 3 things, but there are only really 2 variables, so we only got 4 rows. It's an easy one to prove. Okay, so we then move on to, then we do factoring, okay, which is the reverse of distributing. So what we do is we arrange things so that we put the not psi on one side. So we basically look at this thing, and then we look at this thing over here, and say we can apply factoring because they both have the same factor of not psi. So we factor out the not psi. What is left is the not phi and phi itself. So not phi or phi, is now combined into its own little disjunction. So it's the same thing as factoring in multiplication and addition, except in this case it is the Boolean version of that. And then we do the same thing with rho. So now we combine rho or not rho into one part, and then factor out psi by itself. And this is done by combining this expression with the last one, which is this expression here. So by rearranging things, I can now do the factoring. And then we have whatever is left over, after the factoring. After we do the factoring, we end up with, oh, we recognize this thing. This thing is just true because it is not phi or phi, so it is true. So that becomes this one over here. And this thing is exactly the same thing. Rho or not rho is just true. So we now have this thing over here. But that allows us to simplify one step further, because 1 and whatever is just whatever. So we now end up with not psi because of this. And then on the other side, this is psi psi and 1, which is really just psi all by itself. But when you look at this, then we say, oh, this is not psi or psi, which means it is true. But once we have a true in a disjunction, the entire disjunction is going to be true. So this is the end of the proof. Okay, we have proven that this implication is always true. Yep.
Can you explain one more time the not psi or psi part?
On which row of the proof?
The third one from the bottom.
Third one from the bottom. This one?
Yeah.
Okay, this not psi is coming from true and not psi. This psi is coming from psi and true. So I basically, but you can see that I'm really just using the same few rules over and over again. Okay, De Morgan's law, introducing and true. True is whatever expression or the negation of that expression. I kept using those things, but I have to choose where to apply that. Is that making any sense?
Do we have to memorize all those rules for an exam?
The rules themselves are easy to memorize because your exam is going to be open book, open notes. Knowing when to use one is the difficult part. But this proof is important because it shows you that the inference itself is sound. It shows you that this transformation rule is sound because in terms of the actual operator, it comes to the same conclusion. So let's just look at this one more time. What this is saying, this is a transformation rule. What this is saying is, if you can identify one well-formed formula that has a structure of something that looks like this, and another one that is structured like this, then you can come up with a new well-formed formula like this, and add that to all the well-formed formulae that you know is true already. But this is being done in a syntactical way. It's just pattern recognition. Okay. So does it make sense? I can specify any rule for syntactic transformation. The question is the result of the transformation making any sense? Okay. So this proof here, saying that if you look at the meaning of disjunction and conjunction and negation, this expression always implies this expression. In other words, if you know this is true and this is true, you can always come to the conclusion that this is true as well. Okay? We need to know that so that we know that the transformation rule, the inference rule itself is sound. It makes sense. So that's the importance of this particular proof here. And in addition, it also shows you, all the Boolean algebra stuff that you can use in order to prove something. So are we good so far on resolution? One single rule, one single inference rule is all that you need. Yep.
So on the first step, you negated the left side and did a conjunction with what was on the right side?
Disjunction to the...
Can you always do that? If it's
Yes, because that's the definition of implication.
Okay.
Because A implies B, by definition, is the same thing as not A or B. So that's exactly what I did, except the A part is kind of complex. That's why you have to kind of count the parentheses to know how many nesting levels are we dealing with. Okay. Well, this is really great. I did not choose this T-shirt based on what I think is what I'll be teaching today. One ring to rule them all. What ring are we talking about? That one inference rule. So instead of having all the 9 rings, distributed to all the different races, we only need one ring now. So as it turns out, my T-shirt actually matches what I'm teaching today. What? Yeah, this is the ring. This is the Eye of Sauron. They are holding hands because they like to be together, because the eye is always looking for the ring. Okay.
Oh.
We need to spend one class to watch the movie.
Like 3 classes.
Sorry?
It's like 3 classes.
3 classes, right. Yep. We can fast forward to only the important parts, right? Okay. Now, the cool thing about this is you can, the next thing we need to do is so this is one really important step. The next question is, this transformation rule is useful, but how do we use it to prove theorems? We still have that missing step, okay? So when you want to use this to prove theorems, we need one more thing to get this to work. The one more thing that we need to do get it to work is proof by contradiction. Now, how do we prove by contradiction? Okay, so to explain proof by contradiction, I can use the whiteboard, or I can use the whiteboard. Okay, so proof by contradiction is basically saying it starts with this. P implies Q is saying the same thing as not Q implies not P. Okay, this is the root of your proof by contradiction. Now, is that right? I mean, can we prove that this expression is really the same thing as that expression? How do we prove it? Exactly. Truth table. So this is really important because truth table is a very, very useful tool when it comes to Boolean expressions. And it's not just this class that you will need to deal with Boolean expressions. When you take a class in computer engineering, logic gates, logic design, and stuff like that, they all have to use truth tables. Okay. So with P implies Q, we already know this is true, this is false, this is true. Okay, done. Now we reverse it. Okay, not Q implies not P. So let's take a look not Q implies not P. This one is good because Q is false, P is false, so that makes the negation of both of them true. True implies true is true, so we're good. This one is going to be good too. This is going to be true because Q is true on this row, so not Q is going to be false. False implies whatever is always true. Okay, so we got that, and we can also get this one too because of the same reason. So the one in between is the one where Q is false, so not Q is true. P is true, not P is false. So now we have true implies false, which is false. Wow, okay, so P implies Q is really the same thing as not Q implies not P. There's another way to prove this too, okay? The other way to prove this is using Boolean algebra. So in that case, you actually spell out the proof. Okay, I can show you how you can spell out the proof itself. Okay, so P implies Q is the same thing as not P or Q, right? Because that's just the definition of implication. Is that okay? All right. So with this, we can move on to the next step. So we can say, can we do that? It's just changing the positions, but because disjunction is commutative, we can always exchange positions without changing the meaning of the expression. And then we say we put a double negation in front of Q. Would that be okay? The negation of Q is Q. Okay, that's okay. So now we can just say, oh, wait, hold on a second here. I can now see this as the negation of Q or negation of P. In other words, we are seeing something like not blah blah or something. So by the definition of implication, now we can say not Q, which is this part here, implies not P. So now we have two different proofs. One is using truth table, and the other one is just using Boolean algebra to prove exactly the same thing. Questions? No questions? Okay. All right. So right here we have a corollary, which is basically a small theorem. So the theorem is basically saying, okay, if you know that P implies Q is true, then you can always add something to both sides. You can always say, oh, that means P and R implies Q and R. Whatever R is, doesn't even matter, okay? As long as you just add and R on both sides of the implication, it will be fine. Is that okay? And the proof of this is over here. Okay, so if I'm not going to spell out this particular proof, but you guys can look at each look at each row and see how it relates to the row before. So this would be a good exercise for you guys to try to at least recognize what Boolean algebra rule did I use for each row, to transform one row to the next row. Okay, so once again, this is not assigned as a homework assignment, but I think if you just kind of go through this and be able to identify, oh, okay, Tax just applied this, okay, the definition of implication, or De Morgan's law, or the distributive law of Boolean algebra, or something like that, that will be really helpful because it will help you understand how those rules are applied and in what cases which rule is going to be helpful. So that's going to be helpful. So now with proof by contradiction, we make use of this thing first. So we make use of P implies Q implies P and R implies Q and R. So we make use of that, and then we assume that psi implies phi to begin with. In this case, this is the collection of everything that we know of. In other words, psi is representing all the axioms, all the known facts that we already know at that point. Phi, on the other hand, is representing the theorem, the very theorem that you are trying to prove. Is that okay? we want to show this. We want to show this implication is always true, because that is what it means when you're proving something in mathematics. Okay, so you're given a whole bunch of axioms, which is represented by a huge conjunction, which is now our psi. You're given the theorem that you're trying to prove, which is our phi in this case, and you're trying to prove that this implication is always true. That is a mathematical proof. Okay, you can go from known facts to the theorem that you are trying to prove. Is that part okay? Sort of. Okay. What is a proof in mathematics, in any class, not just this one, but also in your calculus class, your algebra class, your trig class, and so on? What is a proof? What is it representing? Go ahead. Transformation? Transformation is kind of syntactic, but it's a long chain of reasoning, right? You know, a proof is a long chain of reasoning. But what is that chain trying to connect? On one end, you have the theorem that you're trying to prove. We know that end. What is the other end of this chain or web? You know, because it's more like a web than anything else. What is on the other end of this web? What are you connecting the theorem to? The axioms, okay? All the things that we know, all the things that is given to be true. That is a mathematical proof. Is that okay? But what does each link look like in that web? In other words, if you were to draw a map of a mathematical proof, doesn't matter what kind of subject you're dealing with, what type of math you're dealing with, but when you draw a map of a mathematical proof, what do you get? On one side, you have all the axioms, all the things that are known to be true. On the other side, you have the theorem that you're trying to prove, which is represented by a single point. And we already know that this is a web, okay, because there are things where the axioms would lead to the same thing, you know, these will lead to the same thing, and then these will combine, and then they can branch out again, and then recombine with something else, eventually leading to this. The question is, what is each of these links? What does it look like? It's an implication. Okay? Now, can it be an equivalence? Yes. If it can be equivalence, it's even better, but it doesn't have to be equivalence. It only needs to be, each one only needs to be an implication, 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 implication. They only have the implications. Because if you have a whole web like this of implications, that means eventually you can imply the result here by only using the known facts. Is that okay? In other words, every mathematical proof is really a long chain of implications.
Why is it implication? Why is it implication?
Because what does the implication do? Implication says what? A implies B. Okay, so let's look at the definition of implication. 0, 0, 1, 1 for A, 0, 1, 0, 1 for B. The implication itself is true, 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 false, true, like that, right? That's the definition of implication. So in a mathematical proof, we are given that these things are true to begin with. Is that okay? Which basically means along each step, these are all true stuff. So that means this is true, 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 and this is true. So the implication allows you to connect the truthfulness of the axioms and other things that you already know is true, including other theorems, right, to the truthfulness of the one expression that you need to prove. Okay? Now, if all of these things are bidirectional, it's great because that means you can go in both directions. But in normal proofs, you just needed to go in one direction, so implication is enough. Yep.
Is it the same as saying syntactic entailment connects them all?
This is semantic entailment. Because semantic entailment is based on the meaning of the operators. But this picture is not only applicable in this class. These things can be concepts in calculus, can be concepts in trigonometry, can be concepts in linear algebra, Okay, it doesn't even matter because the structure of a proof is always like this, regardless of the actual field that you're working in. Is that okay? So that means this is important because this is representing this long chain here. The psi is really a collection, a conjunction of all of these things, and then the phi is the end product. This is the theorem that we are trying to arrive at. So this is the proof. Okay, if we can find this implication, we are done. That proof is done. So proving is about establishing that one single long implication. Now, if this implication does hold true, which means there's a picture, there's a map like this to eventually use implications to connect the axioms all the way down to the theorem that you're trying to prove, then we can also make this conclusion. The negation of the theorem is going to imply the negation of the conjunction of all of the facts that we already know. Well, how do we know that? We just proved it. This is our proof. P implies Q is exactly the same thing as not Q implies not P. Well, what if P is representing a huge big conjunction of everything that we already know, and what if Q is representing the theorem that we are proving? It still works the same way. You negate the theorem. If the theorem itself is true, then it will lead to the negation of the facts that you start with. And that is the basis of proof by contradiction. You start with the negation of the theorem first, and then you arrive at some kind of a contradiction. Is that okay? So with this one, okay, so how are we going to use the corollary that we just established a little bit earlier? Okay, so we take a look at this and say, okay, so according to that little small theorem, I can add any component to both sides, and as long as it is the same thing using a conjunction on both sides, the result would still be okay, right? So what if I were to do a conjunction here with P itself? Okay, so I will do an and P on one side, and I'll do an and P on the other side. What are we getting here? Do you recognize something? What is this? We saw this a little bit early in this class because one of you guys asked me. It's always false. Okay. So that means if you negate a theorem, and it is in fact a theorem, if you negate a theorem, you do a conjunction with everything that is known up to that point, it will lead to a contradiction. Something that always leads to false is called a contradiction. And this is the basis of proof by contradiction. You start off with the negated theorem, you combine the negated theorem with all the same assumptions that you start off with, and you should come up with a contradiction, something that is always false. Is that making any sense? Are the components connecting? Okay, very good. Right. Why is this a big deal? I cannot believe it. I actually did not read from my own notes, and apparently I used that phrase a lot. But why is this a big deal? What is the importance of proof by contradiction in the context of resolution and CNF? Because now we got the three components, but how are these three components connected? How do they combine to be useful at all? So let's go ahead and take a look at these three components. If you want to write this down, you can write this down, but it's all kind of in the notes, but the connection, you might want to write down the connection itself. So right now we got three things. We got CNF, and the significance of CNF is every well-formed formula can be transformed into a CNF. Give me any well-formed formula as a Boolean expression, we can convert it into a CNF, which is great, which means CNF is just as expressive as any well-formed formula. Okay? So we can represent everything that we need to represent. First thing, resolution. Resolution. Resolution is basically saying if you have something that looks like this, okay, you can always transform that into rho or phi in this case. In other words, the one component that is negated on one side but not negated on the other side, quote unquote, cancels out. And then you keep the rest. It's kind of like concatenation in a way. Is that okay? That's resolution. And this is the only transformation rule that we'll need. We first express everything in CNF, and we have one single rule left, one single inference rule that is needed, which is resolution. And then the third piece is proof by contradiction. Okay? So the third piece is proof by contradiction. Okay, so how are all of these pieces connected? The first one is easy, okay? If you're given any facts, first transform that into a CNF. Second one, resolution. Okay, we're not quite sure where to use resolution, but we also know that we want to use proof by contradiction. When you use proof by contradiction, what do you think is the end result? All successful proofs by contradiction gets to the same destination, which is false. Doesn't hurt to draw a picture. So in this case, let's say we are trying to prove a theorem where psi is representing all the known facts, and we want to show that psi is leading to phi, which is the theorem that we're trying to prove. Okay, same letters meaning the same thing as in the notes. Okay, so what is that meaning? That means that we start with all the known facts. So we have psi. So psi in this case is represented by multiple points because we have a whole lot of axioms, a whole lot of theorems already known to be true, and so on and so forth. All of those things combine to be phi. Is that okay? And then we have psi. So we have phi, which is representing the theorem that we're trying to prove. But we're not gonna go. We don't do it this way. Okay. The traditional way is to go in this direction. Okay. You start off with psi, and then use all the other rules to try to transform everything eventually into phi. We're not going to do this anymore. Instead, we'll put the negation of phi over here as a starting point. And then we say, can we get here? There's only one destination point regardless of what you're trying to prove when you apply proof by contradiction. The destination is always false. That is proof by contradiction. Can we do this? If we can, that shows that phi is in fact a theorem, because by combining the theorem and all the known facts, we get to a contradiction. If you cannot get here, that means phi itself is not a theorem. It does not follow the given facts. Is that okay? That's proof by contradiction. We got CNF, we got resolution. So how do these things relate to each other? This entire thing is one gigantic CNF. So we start off with one gigantic CNF, which is representing everything that is in iota. Okay? So these are the things that are in iota, which are the known facts, right? We also have to include the negation of the theorem that we're trying to prove, but it has to be in the form of a CNF. So this is one gigantic CNF. The question now is, how do we get to the contradiction? What do we apply? There's only one thing we can apply in this case.
Resolution.
Resolution, exactly. So every single step that we go through is resolution. Resolution, 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 resolution. Combine resolution. 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 And so on. and then eventually the last resolution will end up with false. Hmm? Oh yeah, the notes has examples. It's already there. We got examples. At the bottom of the screen, there's example 1, okay? Okay, so here's an example. So the example is telling us that we throw the ingredients into the pot. So in this case, we know the facts already. The facts are P implies R. We know the facts are P or Q is true, always true in this particular system. We know that the negation of Q and R is always true. And we also know that the negation of R implies Q is always true. So these 4 things are the initial things that we know are true. Okay, this is known to be true, this is known to be true, this is known to be true, and this is also known to be true. They are all in iota. Is that okay? So the first thing we need to do is to transform each one into a CNF. That's a CNF. This is a CNF to begin with. This is a CNF. And this one is a little bit nastier, but eventually we get to the CNF that we need. Is that okay? So now we have 4 individual pieces of CNF. So how do you combine CNFs into a gigantic, bigger CNF? Just AND them all together. Okay? That's one really good thing about CNFs is if you started with a CNF on one side, you started with a CNF on the other side, the conjunction of those 2 CNFs has to be a CNF. Okay? So this is great. Okay? So now we know the CNF itself. So this entire pot is a CNF, and the CNF looks kind of like this. Okay? Any surprises here? Let's check. This is the first chunk. It becomes a part of the final CNF. This is another chunk. It becomes the second piece of the final CNF. This is the third chunk, which becomes the third part of the CNF. This one becomes 2 different chunks because it is a CNF itself using conjunction. So when you combine that into the gigantic CNF, each individual component becomes a component of the final CNF. Okay? All right. Yep.
So there was a conjunction between P and Q. In the resulting CNF, you have P separated.
Yes.
Okay.
Yep. Okay. And by the way, in this case, this is the theorem that we're trying to prove. We are trying to prove that R implies Q. That is the theorem that we're trying to prove. But we have to negate it first because in a proof by contradiction, you have to throw the negation of the theorem into the gigantic CNF to begin with. So that's why we have to negate it first. But this is the CNF. So with this as a CNF, how do we apply resolution? Okay, so this I use the underlines to indicate what we are combining to end up with what. So we have P or Q with this expression. We have not Q all by itself over here. The Q's would, the Q and the not Q, would make the connection. But then we concatenate the rest of each expression. But in this case, we only have P left. So P is the new well-formed formula that we are adding into the system. P itself is the result of applying resolution. Is that okay? Let's slow down here and make sure that this is okay. Okay? So I'll give you the 2 expressions as the starting ingredients. One ingredient is this one on one side, and then the other ingredient is this one on that same side. Applying resolution, I end up with this. Okay, let's check whether that makes sense or not. Okay? So what I'll do on the whiteboard is I'm going to spell out the resolution rule itself. The resolution rule itself, do I still have it here? Yes, I do. Excellent. Okay, so I still have the resolution rule here. So we'll try to match those 2 expressions and see if it works or not. So in this case, we have what is the component that on one side is non-negated, on the other side is negated. Look at the single underline.
Q.
The Q, okay? So we have Q on one side, we have the negation of Q on the other side. So the Q is basically our psi in this case. Okay, so we have not Q over here, and then we have Q over here. Now once you lock down what is Q, what is the rest? What is rho? Rho is associated with not Q. Is there anything attached to not Q? Is there anything attached here that is implicit? You can always say or something, right? What is the identity of disjunction in Boolean algebra? You can say blah, 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 or this thing, and it will always preserve the meaning of the original blah, blah, blah. Or zero, very good. Okay, so we have a zero or not Q on one side. And then what about phi here? What is our phi in this case? Phi is associated with the non-negative version of the variable, which is P. Very good, okay. And this is a syntactic transformation, which means whatever rho is a zero. We preserve that. And this is phi, whatever phi is P, right? Is that okay? So we end up with 0 or P, but 0 is false, or whatever is always whatever, right? So that means our result from the transformation or the result of the inference is just P all by itself. So for every single step here, I use the same notation. The single underline is indicating the connecting piece, and then the double underline is indicating the resulting expression, okay? So after we get P, we add P to the pool, and now we can say, what else can we do? Let's see. So this is a not P over here, this is a single P over here, so we can look at these two, apply resolution, and end up with R or Q. So now what can we do about this whole thing? Well, let's see. We have R here, we have not R over here, so now we can combine not P or not Q. So not P or not Q becomes a new expression. And what else can we possibly do? Well, we got a Q over here, we got a not Q over here. Combine these two expressions, so now it becomes P or not R, and that's it. Okay? So right now at this point, you can try anything. It won't add any new terms to this whole thing. How much work do we need to go through to show that there are no new expressions to result in resolution? Okay, first of all, is it an infinite loop? If you were to write a program to analyze a conjunction, a CNF like this, to see if you can apply any resolution that will end up with a new expression, how would you write that program? Can it be done step by step? In other words, can I just look at the first one first and I ask, okay, can anyone connect with the not P over here? Yep, this guy can connect with the not P, but we have done it already. This one can combine with the not P, and it results in R, which is already here to begin with. Doesn't give us anything new, right? What else can combine with this not P? Where's my other P? Oh, here's another P over here. So this P can combine with this not P over here, and then we end up with R or not R, which is 1, which is true, is not useful. Because this whole thing is one conjunctive normal form. You're just adding a and true to the end of the whole thing. Doesn't change anything. So now we are done with this not P of the first expression. Now we look at the second variable of the first expression, and then we go like, okay, what can combine with this R? Oh, here's a not R. So when we combine this R with this not R, we should end up with not P or not Q. Ah, but we got that here already. It's nothing new. What else can combine with this R? Nope, this is not negated. This one is negated. We can try to combine this one. So we end up with P or not P again, which is just true. It doesn't change the meaning of the entire thing. It is useless, right? So now we have exhausted everything that we can possibly do with the first expression. We move on to the second expression. What can combine with this P? Oh, we got this not P over here, right? Okay, so if we combine this not P with this P over here, then we concatenate the Q and the not Q over here. Q or not Q is just true. You're adding an and true to the end of this entire expression. Doesn't change the meaning at all. It is not useful. But I can keep doing this, but you can see I have to end at some point, because all I'm doing is going from left to right, looking at each and every single component of each disjunction and see what can combine with that, and then see whether the result is something that is new or not. But once I get all the way to the end, and I determine that I cannot add any useful term to this whole thing, what is the conclusion? I'm done. But did I get to the contradiction? Did I get to false? No. That means the theorem, the proposed theorem, is not a theorem. It is not a result of the given facts. But you can see how it has to end. Now, you might be able to use caching and some other clever data structure to make it go faster instead of exhaustively, sequentially going through everything. But eventually, it has to end. Even if you go for the slowest approach, you will still have to recognize and go like, we're done. We cannot make any new terms anymore. That is the value of these three things combined. CNF to represent the facts that we already know, resolution as the only inference rule that we'll ever need, and the technique of proof by contradiction, so that we have one single goal that we are trying to get to, which is that false. Okay, so are we making the connections at a higher level, not just the mechanism itself, but the rationale behind this whole thing? Okay, very good. So this is the second example. So the second example is, this is a disappointing thing because that thing, the proposed theorem turned out not to be a theorem. So can we prove something that is actually a theorem? Well, as it turns out, this is an actual theorem. So what we do is we have to negate it first so that we end up with the negation of the theorem itself. And then we have to transform that into a CNF so that we can combine that with the rest of the well-formed formulae. And if you take this thing, the first thing you do is this. Okay, from here to here is by definition of implication, and then from here to here is by De Morgan's law, and then from here to here is just by taking out the double negation. Is that okay? So now we add these two components into our CNF. So our initial CNF is now this part. Okay? That's our starting point, which is represented by this particular square over here. When we apply resolution, to the Q and the not Q that are underlined. And by doing that, we are combining the P and the not R, which are basically the leftover terms of the two terms. So in this case, we end up with this new term, which is P or not R. And then in the second step, I choose to combine this not P with this P over here, which will end up with a not R all by itself. And then in the third step, I apply resolution based on this R and this not R here. And this resolution ends up with a 0, ends up with a false. That's because R is implicitly R or 0. Not R is implicitly not R or 0. So when you combine R or 0 and not R or 0, then you have 0 or 0 left. 0 is false. False or false is false, and that's why we end up with a false. Well, once we get to a false, we can stop, because that's what we're looking for. Yep.
So, proving that contradiction only uses resolution.
No, in this particular case, when you express everything as a CNF, then you only use resolution to move forward and see if you can end up with a contradiction. Now, when you're using proof by contradiction in general, then you apply some other logic to make these connections. But when you're dealing with CNF, then every single link is a resolution step. Okay. Are there any questions about all of these things? Because you have your first homework assignment, well, on CNF. Okay, so let me show you your homework assignment, which is due in a week. I don't think it's going to be too much of a challenge. But if you do feel that it's a little bit too ugly, come talk to me and I'll help you out. So what you need to do, the first assignment related to this topic is not a proof. Okay, all I need you to do is to turn these three expressions into a single CNF. That's all. Okay. So what you need to do is to transform each one into a CNF first. So you have to look at this expression and go, okay, I need to transform this into a CNF. I need to look at this and transform that into a CNF. And I need to transform this into a CNF as well. Once you have the three individual CNFs, then you make a bigger conjunction of those CNFs, and that's the answer to this particular question. There's nothing to prove, no resolution involved in this case. Yep?
Just being clear, I can use the C++ operators instead.
Right. So so to help you out, because I know typing \wedge and \v with all the parentheses is not exactly very friendly. So what I allow you guys to do is to use the quote-unquote multiplication to mean conjunction. So P and Q can be written as PQ, and then the addition symbol is used to represent disjunction. So P or Q can be written as P plus Q. And then to simplify negation, you can borrow the symbol from C++, which is the exclamation point. If you prefer to do all the wedges and that's fine with me too. I just thought this is a little bit easier for you guys to type without having to use the LaTeX format and stuff like that. But if you choose to do the whole LaTeX thing, hey, more power to you. So are there any questions about the homework assignment or the concepts that we have talked about today? No questions? Okay, there are three levels of questions that you need to ask as you step out of the classroom, go to your car, okay? Or get into your ride. Three questions. Just think about those three questions. The first one, which is the most important one, is why, okay? Why are we talking about this? What does this have to do with anything like your career, your employment, your future, okay? The second question you have to ask is, what is this? Okay, what is CNF resolution and proof by contradiction? Why are they hanging out together? Okay, and then the third question, which is going to take a lot longer to answer, are the actual mechanisms. How do I turn something into a CNF? How do I apply resolution? How do I know when to stop applying resolution? Those are the hows. So you have to separate those questions into the why, the what, and the how. But you have to keep an eye on the higher level questions first, because otherwise, the mechanisms, the details, is just going to be a little bit, boring, and it's a little bit overwhelming. But so you have to connect it to the what and the why. Alrighty, so that's the end of today's lecture. As far as this class is concerned, the long weekend really does not apply because we don't meet on Fridays, we don't meet on Mondays either. But nonetheless, have a nice long weekend. I'll see you guys next Tuesday.